Lecture correction for omega notation, Tuesday, March 24th, on section 7.2, growth of functions and complexity. The corrected definition of omega notation is here, definition 7.2.2. Let f and g be functions from the positive integers to the positive integers. The function f of n is omega of g of n. We read that as omega of g of n, and denoted by f of n equals omega parentheses g of n close parentheses, or f equals omega g without the independent variable n appearing. If there are positive constants c and n naught such that for any n at least n naught, f of n is at least c of g of n. Now, the original that I went over earlier today, the errors are in the red boxes. So we need to add positive to make sure that the constants c and n naught are positive constants. And this constant c goes on the right side of this inequality, not the left side of the inequality. So positive I just plain left out. This c being on the right side of the inequality. This is a switch from the last time I ran this course. The book had it on the left side of the inequality, and I missed the fact that they switched it back to the right side of the inequality, which is the better side as far as consistency with the definition of big O. All right, so these are now corrected. They are corrected on the activity PDF that's posted and on the annotated lecture notes from today that are also posted in the G Drive folder. To get to that, you would just navigate to the G Drive folder. That link I will post shortly at the top of the homework log page. Now, let's do two examples. Example 1, f of n equals 5n squared minus 3n plus 8 is omega of g of n, where g of n is n squared. That's what we're about to show. We can pick n naught is equal to 1, c equals to 2. In fact, you could choose any n naught c element of the Cartesian product of, say, z plus cross the interval from 0 to 2, including 2 but not 0. That means any pair n naught c works where n naught is a positive integer and c is a constant strictly greater than 0, at most 2. Some other choices will work, but this is a huge Cartesian product of values that would work. Remember, this is an existence proof. We only need one pair. So with n naught equals 1, c equals 2, let's make this observation. 3n squared minus 3n is certainly greater than or equal to 0 for all n at least 1, which is our n naught value. Using this fact, let's express f of n, which is 5n squared minus 3n plus 8. Express this as 2n squared plus the 3n squared that we borrowed from 5n squared minus 3n plus 8. Now this in parentheses, 3n squared minus 3n, is at least 0. So we can say that this entire expression is greater than or equal to 2n squared plus 8, and that would hold for all n at least 1. Now 2n squared plus 8 is at least 2n squared, which is at least twice g of n, because g of n is n squared. And this 2 here is the c that we chose to begin with. Therefore, by definition, f is omega of g. Example 2 is a little bit more challenging because the negative 10n in the middle of the f function has constant negative 10 that is larger in magnitude than the constant 5 that's the leading constant. Of course, negative 10 is opposite in sign, so that's what's going to cause the trouble. So we have to be a little more careful in regrouping things. We want to show that this f of n is 5n squared minus 10n plus 8, is omega g of n, where g of n is n squared. First, we observe n squared minus 10n is greater than or equal to 0 for all n at least 10. If you were to plot this, n squared minus 10n, you would see that it has roots at n equals 0 and n equals 10.
You can think of this expression as an upward pointing parabola with roots at 0 and 10.
and therefore the expression is at least 0 when the value of n is at least the rightmost root, that is 10. We take n naught equal to 10 and c equal to 4. And with these choices, f of n is equal to 5n squared minus 10n plus 8 is equal to 4n squared plus n squared minus 10n plus 8, where we've regrouped as n squared minus 10n in the middle, which is at least 0 for n at least 10. This altogether is at least 4n squared plus 8, and then dropping the 8, this is at least 4 times n squared, where 4 times n squared is written with the c as the constant multiple, and the n squared is equal to g of n. So this whole inequality holds, that is, in summary, fn is at least 4 times g of n for all n at least 10, the value of n naught. Therefore, by definition, f is omega of g.